As a mechanical engineer, especially as a design engineer, understanding of steel hardening process is extremely important because as a designer, this is our responsibility to specify the appropriate hardening method and the hardness value HRC value for the steel components in their manufacturing drawings, particularly for the tooling components like punching tool, bending tool, flaring tool, clinching tool, riveting tools, marking tools, cutting tools like cutters, drills, and there are a lot more. And these tools goes under cyclic load, and at the same time they must maintain their perfect shape without deformation. Also the component which is designed to slide over the other components like guide rails, LM shaft, cam floors, bushings, bearings, locating pins. Also the components like gears, sprocket, spline, mold and die, which are frequently goes under cyclic load. These components must be hardened adequately to maintain their perfect shape and the sharp edges, even under the heavy and sudden loads. So to ensure the proper function and provide durable life to the toolings and sliding components, we must harden this component with appropriate hardening method to an optimum hardness level. And this is the point where lots of questions with lots of confusions arise for a design engineer. Like how to select the appropriate hardening method, where we should recommend full hardening, where we should recommend case hardening, or oil hardening, or induction hardening, or also we should do tempering. And what should be the optimum hardness level? What should be the hardness level HRC for the tooling components like bending tool or cutting tools, and what should be the hardness level HRC for a sliding components? So hi there, this is Ayush from Master Mechanical Design, and this video is a complete guide to steel hardening. In this video, we will cover everything that you need to know about steel hardening as a mechanical design engineer. Like what is hardness, what are the types of material hardness, and then how to measure these hardness, what are the popular hardness testings and their scales, and then where to specify which hardness scale, like where to specify HRC and where to specify HRB or HB or Brinell scale. Also how to calculate HRC hardness, and then how much initial hardness we can expect from various grade of steel raw materials. What are the factors which makes one steel grade harder than other steel grade? What is the chemistry behind the steel hardness, and then how to increase the initial hardness of the steels using different method of steel hardening, and then how to select a suitable hardening method for a component for application. What is the basis of the selecting right hardness method, and also how to determine the optimum hardness value HRC value for the toolings and sliding components. And here we have to understand that for toolings and sliding components, only hardness is not an essential parameter. The tools materials must be also tough and wear resistance. So the selection of suitable steel grade is also very important for the toolings and sliding components. And everything is well chaptered as per the time stamp. So let's start from what is hardness. What is the meaning of hardness and how we can define the hardness? So hardness is measured to resistance the localized plastic deformation. What this means is how much force a material can withstand without getting plastic deformation, localized plastic deformation. Not the overall plastic deformation, but the localized plastic deformation, like a scratching, penetration, indentation. In simple words, more hardness of material means more resistance to plastic deformation. So after which point plastic deformation starts? You guessed it right, after the yield strength point. After yield strength limit of material means the material which has higher yield strength will have more hardness. For example, plain carbon steel yield strength range between 250 to 550 megapascal. Pure aluminum yield strength range from 35 to 50 megapascal, while a titanium alloy yield strength range from 800 to 900 megapascal. So steel is more harder than pure aluminum, and titanium alloy is much harder than the steel. And this is estimation of hardness in terms of yield strength. Here hardness H is in terms of contact pressure. Contact pressure means the load divided by projected contact area. C is 3 for the metals like steel and 1.5 for the glass. But this is an quite approximation because the behavior of a solid material under force is very complex. Therefore, hardness can be measured in 3 different ways: a scratch, indentation, and rebound. So a scratch hardness is a measure to how resistant a material is to scratching. A scratching means fracture or permanent plastic deformation due to friction from a sharp object. And the concept is an object made of harder material can scratch a object made of softer material. Therefore, a sharp diamond piece can scratch on steel material, but we cannot scratch a diamond piece with a sharp steel edge. So in India, there is a phrase, only diamonds cut diamonds. Of course, we can break the diamonds via a steel piece like with a steel hammer because diamond is relatively brittle, but we cannot scratch a diamond piece with a steel sharp edge. I have never tried, but the diamond is much harder than the steel. And to measure the scratch hardness, Mohs scale is used. Mohs scale is collection box of different minerals. Minerals on the scale of hardness from 1 to 10. For example, diamond has highest hardness, which is 10, and then corundum has 9, and so on up to talc, which has hardness 1. And the process of hardness testing is quite simple. We start by trying to scratch with minerals which has lowest absolute hardness as per rough estimation, and then we go up one by one. And the first minerals which successfully scratch the component is considered as the hardness of that component material. And also there is a conversion table for this scratched hardness into Vickers hardness scale. Vickers hardness scale is the widest scales among all the hardness scales. We will get to it later in this video. So the scratch hardness measurement is very useful in coating and surface treatment industry to ensure the hardness of the coatings and surface treatment. But for general engineering purposes, we usually measure indentation hardness. Indentation hardness measures the resistance of material to deform due to a constant compression load from a sharp object, means resistance to penetration. So to measure the indentation hardness, we press a sharp indicator over the component with a known force, and we calculate the hardness of component on the basis of depth of penetration made by the indicator under that known force. Indicators usually made of either diamond or very hard material, and the shape of indicator can be spiroconical or tiny bowl shape depending on the type of hardness scale. If the indicator penetration in component is high, then it means that component is relatively soft compared to the component which has less penetration. And on the basis of amount of pressing force, indentation hardness testing is divided into 3 classes: macro, micro, and nano indentation testing. Micro indentation testing used for the engineering purposes, pressing load larger than 1 kgf, approximate 10 Newton. Macro and nano indentation testing used for the scientific and medical purposes, pressing loads less than 2 Newton, means 200 gram force. So we will not talk about macro and nano indentation hardness testing. We are engineer, not the scientist. So let's only focus on macro indentation hardness testing. And there are various testing machines for macro indentation hardness testing, and they measure the hardness on different scales such as Rockwell, Vickers, and Brinell scale. Now, before we dive into each hardness scale, let me clarify also in case you are wondering that why there are so many scales instead of just one. Because later on you will notice that within some scales, like in Rockwell hardness scale, There are also some different subscales like HRA, HRB, HRC, and so on. So to understand it, think of these three main hardness scales as a size or distance measuring scales, such as metric and imperial unit, inch unit. And as the metric units, means millimeter, centimeter, are common in Japan, India, and in Europe, while imperial unit, inch unit, are popular in USA. Similarly, Rockwell scale is popular in USA and in India, while Vickers hardness scale, HV scale, is more common in Japan and in European countries. So these are just different hardness scale system, and there is also approximation conversion from one scale to another scale. I will leave this table in video description. And for the subscales, think of the subscales like HRA, HRB, HRC are the different units of the one main measuring system. Like in metric system, for fairly long distance, we use tape in meter. But for the shorter distance, we use vernier caliper in millimeter, right? Because if we will try to measure the shorter distance with measuring tape in meters, then the accuracy will be not good. Similarly, in material hardness, if we will try to measure the whole range of hardness, that is from very soft to very hard with a single instrument on a single scale, then the measurement accuracy will be not good. So Rockwell hardness HRB is used for the soft material range and HRC is used for the harder material range. I hope this is clear to you. Now the Vickers hardness testing HV scale. So Vickers hardness testing HV scale is one of the widest scale. Therefore HV scale is used to measure the hardness of all kinds of material like steel, aluminum, ceramic, plastic, everything. It is highly accurate for thin material and small samples, particularly popular in Japan in European countries. I'm sure because I have often find HV hardness scale in Japanese product technical data sheets. The second is Rockwell hardness scale, which is most popular in USA and in India. This method is fast because it provides direct readings and required minimum setup time. The Rockwell hardness scales include subscales like HRA, HRB, HRC, D, and many more. Among these all scales, HRB and HRC are widely used. HRB, B stands for ball indicator. The measured load, the penetration under known force is 100 kg and mostly used for relatively soft material like aluminum. HRC, C stands for conical indicator and measured loads 150 kgf. Look, you don't have to memorize any numerical value. I'm explaining just because to establish that why these different hardness scales are exist and their purposes. For example, HRB is used to indicate the hardness of soft material, whereas HRC is used for the hard material like steel, hard cast iron or other materials which hardness is greater than 100 HRB. So we mostly use HRC hardness scale for the toolings and sliding components made of steel. However, Rockwell hardness test is not suitable for the very thin material for a small sample. For the thin steel materials, it is better to use Vickers hardness scale, HV scale. And here is the formula for calculate Rockwell hardness, where HR is the Rockwell hardness, N and H is the scale factor, a specific constant for each scale, because different scales use different applied load and type of indicator and the size of indicator. For example, let's say we have to measure the hardness of a steel piece in HRC scale, and we obtain the penetration depth of 100 micron, 0.1 mm, then we can calculate the HRC hardness as HRC equal to N, which is 100 for the C scale, minus under bracket H, which is 500 for the C scale, into D, the penetration depth 0.1. So the hardness will be 50 HRC. I hope this is so much clear to you. Next is Brinell scale, indicated by BHN or HBW, which has different formulas to calculate the hardness. These testings use ball indicators made of tungsten carbide. Brinell scale is correlated with the ultimate tensile strength UTS of the material. For steel, if we will divide the Brinell scale value by the 2, it will provide approximate UTS in KSI. The Brinell scale is most common used for the material with coarse structures such as casted part. And this is it for the indentation hardness and their measuring unit. Now take a moment to understand the rebound hardness. So the hardness can be also measured in terms of bouncing ability, known as rebound hardness or dynamic hardness. And the concept is a harder material will bounce more than a softer material. And the device is for this measurement is called a scleroscope. And there are also other methods of measuring rebound hardness, including ultrasonic contact device and other compact devices. And it is important to note that rebound hardness measurement is related to elasticity of the material, not to the plasticity of the material. And rebound hardness is not widely used for the engineering purposes. So just for a quick recap, hardness of a material measures its resistance against plastic deformation, localized plastic deformation such as scratching and indentation. And the hardness can be measured and expressed in 3 different ways: a scratch hardness, indentation hardness, and rebound hardness. A scratch hardening is mainly used in coating and surface treatment industry to check the life of coating against abrasion. Indentation hardness primarily used for the general engineering purposes such as toolings like bending tools, drillings, cutter, gear components, chain, sprockets, bearings, guide rails. Indentation hardness measures the resistance against penetration and the permanent deformation. And there are 3 popular testing for the indentation hardness. Vickers hardness test, HV scale, one of the widest scale and used for all types of material. It provides high accuracy, especially for the thin material and small samples. Rockwell hardness. Rockwell hardness scale, HRC, is used for the harder material like steel, while HRB is used for the relatively soft material like aluminum or brass. Rockwell hardness testing is simple and fast, but not recommended for the thin material. Brinell scale is recommended for the coarse structures like casted iron. And Brinell scale is correlated with the tensile ultimate strength. So as in this video, we will mainly focus on steel hardening. So we will use the HRC as a hardness unit. So what is the hardness of steel? How much HRC hardness? So let's understand it in 2 steps. The first is initial hardness of steel material, means how much hardness we get in various steel grade when we first buy them from market, raw material hardness. Also, what are the factors that contributes hardness in steel grade? Why one steel grade is harder than other steel grade? And then we will understand how to increase the initial hardness of the steel. Our main topic, steel hardening, different method of steel hardening and their selection. So first of all, why steel? Why not just iron, Fe? So pure iron, Fe, typically hardness around 80 to 100 HB. Brinell hardness. In HRC, approximate 0 to 5, relatively very soft. So the pure iron Fe is not enough hard to use in common machine components. So a small amount of carbon up to maximum 2% by weight is added with iron, and this alloy mixing is done in furnace when iron is in liquid soluble form. And the alloy of iron and carbon called carbon steel, often called steel. So yes, in general engineering, we use steel, not pure iron. Carbon from 0.05 to 0.25 considered as low carbon steel, also known as plain carbon steel, usually used in steel profile sections like C-channel, square pipe, angle, and there are a lot more for structural work. And the hardness roughly around 10 to 15 HRC. Then carbon range from 0.3 to 0.6% considered as medium carbon steel. Hardness roughly around 15 to 25 HRC. And the carbon range from 0.6 to 1.4 considered as high carbon steel. hardness roughly around 20 to 30 HRC. If the carbon is more than 2%, then alloy becomes very brittle, and we call it cast iron, not the steel. So this was the first factor of initial hardness in a raw material. A soluble alloy elements like carbon increase the hardness of a steel. In general, more carbon percent means more hardness of a steel raw material, but should not be more than 2%. If you found this video useful so far, please do like the video. Now, some other elements like chromium, magnesium, vanadium, molybdenum are also added to enhance the steel other properties like toughness, wear resistance, temperature resistance, and it's called alloy steel or tool steel like D2, HSS, E31. We will talk about it later in this video. Just for side note, steel has mainly 4 categories. One is carbon steel, alloy steel, tool steel, and stainless steel. If you want a detailed video on a steel grade, please let me know in comment. Now, the initial hardness of the steel raw materials also depends on how it is initially processed and shaped, whether through cold working or hard working. If the steel raw material is shaped through cold working, such as cold rolling or forging, it will be relatively harder. Conversely, if the steel raw material is processed by hot working, like being directly molded into shape, it will be relatively softer. This is because when steel goes under cold working, such as cold rolling, the steel grains experience strain. Steel grains are small crystalline pieces within the steel. So during the cold working, grains experience strain and causing plastic deformation and generate new dislocation. And as the dislocation density increases, so further dislocation moment becomes more difficult because the dislocation hinders each other. And as a result, steel become more harder after the cold working. Also, after the machining operations like millings and turnings, which is also a cold working process, steel hardness may slightly increase for the same region. So just to summarize, a steel raw material typically has hardness around 20 to 40 HRC, depending on the steel grade, depending on the carbon percentage and other alloy percentage, and the raw material work hardening process, cold worked or hard worked. Like CR sheet, cold rolled sheet will have more hardness as compared to unfinished hot worked sheet. And this much hardness, 20 to 40 HRC, is well enough for the machine general components, like structural parts, shaft, mounting brackets, base plates. But when it's come to toolings and sliding component, this much hardness is not enough. We will need to increase the initial hardness of the steel. For the cutting tools like cutters and drills, hardness should be 60 to 65 HRC. So much hardness because cutting tools require high hardness to maintain the sharp cutting edges and resist the wear during the cutting operation. For punching tools, hardness should be 58 to 65 HRC because punching tool is also need high hardness to withstand the impact and shear force during the punching operation. For the marking tool, to punch marking on metallic component, hardness should be 55 to 60 HRC to ensure the precision and durability of the marking tip. For bending tool, 50 to 55 HRC, it is slightly lower hardness range, because bending tools require a balance between hardness and toughness. And for light load operation tools like flaring tool, clinching tool and riveting tool, hardness should be 45 to 50 HRC. It's a lower range hardness because in these tools we need more toughness instead of more hardness, because tools has to withstand high pressing force. And the sharp edges are not needed in this tool unlike cuttings and punching tools. So we can keep the hardness in lower range. Now, for the sliding components, we also need high level hardness to minimize the wear, because a little wear out of material can disturb the accuracy of the sliding rails. So for sliding rails, 50 to 60 HRC, for LM shaft 58 to 62 HRC, for bearings, ball bearings 58 to 65 HRC, for the bushings, steel bushings 40 to 50 HRC. Now, for the gears and splines, 58 to 62 HRC on the teeths. For the sprocket, 55 to 60 HRC, and for cam and floor, 55 to 62 HRC. This is for miniature cam and floor. Now, the molds also need high hardness level to resist the wear from repetitive use and to maintain the precise shape and dimension. So for plastic molds, 48 to 56 HRC, and for die casting mold, 60 to 64 HRC. You don't have to take this note, I will leave this table in video description. And now let's see how we can achieve these hardness levels. What are the process and method of hardening? And what grade of steel we should use for the toolings and sliding components. Also to achieve this much hardness level. But first of all, we should not harden the raw material of the steel. Because if we increase the hardness level of a raw material above roughly 40 HRC, machining operations such as milling, turning will become extremely difficult, or the tooling life will decrease rapidly. Also, the operation like thread tapping will be not possible. The tapping tool could be break inside the threading hole. Additionally, welding will be challenging because hard material take long to melt and fuse. So it is important to complete all the machining process before the hardening process. So there are several methods of steel hardening, and the primary method are quenching and tempering. So quenching is a heat treatment process used to increase the hardness of steel. First, we heat the steel above its upper critical temperature, also called recrystallization temperature, typically between 750 to 950 degree depending on the carbon content. We then hold it at this temperature for a specific period of time, and then we rapidly cool the steel in medium like water, oil or air. And this rapid cooling process is called quenching, and it increases the steel hardness. However, after quenching, steel may be too much brittle for practical use. So after quenching, to address the brittleness of the steel, we do tempering. Tempering is also a heat treatment process to reduce the brittleness while maintaining the hardness. In this process, we reheat the quenched steel to a lower temperature, typically 150 to 650 degree, below recrystallization temperature. And we hold it at this temperature for a specific period of time, and then we cool the steel at controlled moderate rate, but not rapidly. And this much understanding is well enough for an interview. But to fully understand that why steel get harder after quenching, what changes happens inside the steel during the rapid cooling, then we need to understand the chemistry of the steel as a solid material. So steel is a solid material, and solid materials can be categorized in two categories: crystalline solid and non-crystalline solid, also known as amorphous solid. Crystalline solids have atoms and molecules arranged in highly ordered, like FCC or BCC, and repeating patterns that extend in all directions, forming a crystal lattice. For example, steel, aluminum, brass, and diamond are crystalline solid. And on the other hand, amorphous solid lack a long-range ordered arrangement and do not have repeating patterns. For example, polymers like nylon. Now, crystalline solid can be further divided into two categories. One is single crystalline solid, consists of single uninterrupted crystalline lattice through the material. These are used in specialized applications such as semiconductor device and high-performance component. And the second is polycrystalline solid. Most of the metals and ceramics fall in this category. So steel is a polycrystalline solid. So steel as a polycrystalline solid composed of many small crystals, or we can say grains, not a single uninterrupted crystalline structure throughout the steel, because steel goes under heating, cooling, and solidification during the manufacturing, which often leads to formation of multiple grains and each with own orientation. So grains are the small region in a metal with a specific crystalline lattice structure but differ in orientation to the next grain. They are separated, and the hardness of any material depends on the type of crystalline lattice of the grains and the arrangement of the grain's boundary. Some material grains maintain a single crystalline lattice across all the temperature, such as titanium, which grains have BCC structure until it melts. Other like gold, aluminum, copper grains have FCC structure throughout from room temperature to their melting point. And after the melting point of any material which convert into liquid or gas, then there will be no crystal structure. There will be no crystal. There will be no terms like crystal. The atoms and molecules will be float randomly. And this is the region that liquid or gas don't have any shape. They don't have any hardness or strength-like property. Now, steel contains multiple types of crystalline lattice grains throughout the material. And the region of material with uniform crystal lattice structure, grain and composition denoted as phase. But the steel grains crystal lattice structures also change with the temperature. So at different temperature, steel goes under different phase. Here, phase doesn't mean solid, liquid or gas. Actually, phase is only solid, but with different crystal structure and the different composition and having different property. The carbon iron diagram, you remember? So the different phase exist at different temperature and having different crystal structure and property. Like hardness will be different from one phase to different phase. So at room temperature, the raw steel, untreated steel, consists of primarily two phases. One is ferrite, also called as alpha iron. This has BCC, body center cubic crystal structure grains, and it's relatively soft because ferrites contain less amount of carbon percentage and provide ductility to the steel. And another is cementite, Fe3C. This has orthorhombic lattice crystal structure and it is very hard and brittle because it contains so much carbon. So cementites provides the hardness in steel raw material. So to further increase the hardness of steel, we need to alter the crystal structure of the ferrite because this is the soft phase of the steel. So we heat the steel to its recrystallization temperature, typically between 750 to 950 degree depending on the carbon content, and at this temperature the steel phase is known as austenite, gamma iron, and in the austenite phase the FCC structure grains can dissolve more carbon, and as a result the carbon atoms trapped within FCC structure and transforming into body-centered tetragonal BCT structure grains. And this BCT structure grains makes a different phase known as martensite phase of the steel, a phase which is much harder than the ferrite phase. However, the martensite phase BCT is not a stable phase, only stable at high temperature, not at the room temperature. If we slowly cool down the steel, the martensite phase with BCT crystal structure grains revert to a stable ferrite phase with FCC crystal structure grains. So to prevent this, first we give enough time to FCC crystal structure grains to transform into BCT crystal structure grains, which means we keep holding the temperature at austenite phase of the steel for a specific period of time. And then we rapidly cool the steel in water or oil, and the rapid cooling process is called quenching, which gives no time to the carbon atom from escaping the FCC structure. Means carbon atoms get trapped in FCC structure grains and permanently deformed in BCT structure grains. I hope you understood. If not, please let me know in comment. But rapid cooling not only form martensite phase, but also create dislocation and distortion in the grain boundaries. plus also reduce the grain size, which makes steel overall harder and brittle. Now, it doesn't mean that all FCC crystal structure grains change into BCT crystal structure grains, means complete ferrite phase change into martensite phase. Only some FCC crystal structure grains successfully change into BCT crystal structure grains, means into martensite phase. Some are just distorted or some just do not change at all. It just reverts back to the FCC depending on the cooling rate and the carbon percentage in the steel. Fast cooling rates gives less time to the carbon atom to escaping from the FCC structure, means fast cooling rate increase the number of conversion of FCC into BCT, the martensite phase, and the steel grade which will have more carbon percent, then the more carbon atom will trapped within FCC structure and transforming into BCT, the martensite phase. So in order to harden the steel through the quenching process, carbon percent should be at least above 0.3%. And this is the reason we cannot harden all the steels. We cannot harden a steel which has low carbon percent like plain carbon steel. Means to achieve the higher hardness level, we should select the high carbon content steel. And now you can ask that Ayush, if only carbon percent and cooling rate is responsible for the hardness level, so why do we not only use high carbon steel for the all component which to be hardened? Why do we use various steel grades like T2, A2, EN series, HSS? So yes, it's true that carbon is mainly responsible for the hardness level in the steel hardening process. But for the toolings and sliding components, only hardness is not an essential parameter. Tooling components material should have also high wear resistance and age retention property. Also should be tough. And their hardness level should be also maintained at the high temperature. And we call it hot hardness of the tool. And these property we cannot get in simple carbon steel. So we need alloy steel or tool steel. Like tool steel D2 and A2 having very high hardenability up to 60-62 HRC and also high wear resistance and good edge retention and can be used in cutting tools, die, punches. Tool steel like tungsten carbide and cobalt carbide having extremely high hardenability, typically 70 to 19 HRC, ideal for high-speed machines operation and cutting abrasive material. High-speed steel HSS like M2 having very high hardenability up to around 60 to 64 HRC and can be used in drill bit, saw blade and end mills and other cutting tools. EN series material EN31 high hardenability up to around 60 to 64 HRC, used for the bearings, rollers and high wear part. EN24 and EN19, maximum hardness around 54 to 58 HRC after the heat treatment, and that is a complete list. You can download it from the video description. And now let's understand the classification of a steel hardening process. And there are many hardening methods, but I don't want you to feel overwhelmed. For practical understanding, we can divide this process in two main categories, full hardening and case hardening. Full hardening. So as the name suggests, full hardening means hardening the entire component throughout its complete cross section. And this can be only achieved by the quenching process, which involves the heating the steel to its crystallization temperature and then repeat cooling it. And tempering is often included with this process to balance the brittleness of the component after the quenching. Practical example of full hardening are the drills and cutters. So even if the some length of these tools wear out over the time, they can be sharpened and reused because it is full hardened. But the full hardening is not typically useful for slidings and other components. Also not recommended for the thick and large component because it is difficult to heat and then maintain the same temperature throughout the cross section of the component. However, it is better suited for the small components because they can be easily heated in furnace, which is more cost effective. And now, full hardening can be divided based on quenching medium. So let's just start with water quenching, or we can say water hardening. In water quenching, the metal is rapid cooling in water, providing a very fast cooling rate and achieving a high hardness level, typically around 60 to 65 HRC with high carbon steel alloy. However, the rapid cooling rate also introduces a high risk of cracking and distortion due to thermal stress. So water quenching is suitable where high hardness is required and distortion is less critical, such as agricultural tools, hammers, and other simple components. Next is oil quenching or oil hardening. In oil quenching, the metal is cooled in oil, which provides a slower cooling rate than the water. This reduces the risk of cracking and distortion compared to water quenching. However, water quenching has its own challenges, such as fire hazard risk, which require proper handling and disposal of the oil and making it costly as compared to water hardening. Oil quenching is very useful for the medium to high carbon alloy steel, and the components require good balance of hardness and toughness, such as gears, bearings, and crankshaft. Then there is air quenching. In air quenching, the metal is cooled in still or moving air, minimize the risk of crack and distortion. This makes air quenching suitable for the thin and complex part, but the cooling rate is slower and it may not sufficient for the high carbon steel. Air quenching is ideal for the air hardening steel, high speed steel, and large components like shaft and forging. And there are also other methods like polymer quenching, which provide a cooling rate between water and oil. And then we have salt bath quenching, where metal is immersed in molten salt bath, providing uniform and controlled cooling. The main advantage of the salt bath quenching is providing very uniform and controlled cooling, which minimizes the thermal stress. And this method is used for the precision components required uniform hardness and minimum distortion, such as aerospace components and high precision tools. So just to summarize, if component design distortion is less critical like simple components, then water hardening is good choice. For the general purpose components and complex design like tooling components and gears, oil hardening is preferred. For large component, while oil or water hardening is not feasible and extreme hardness isn't necessary, then air hardening is suitable. For the very precise component such as aerospace component and high precision tools, salt bath quenching is suitable. But also keep in mind that it might be possible that all types of hardening process may not be available at your place. So choose wisely and also choose as per the cost. Now the case hardening, or we can say surface hardening. So it involves the hardening only the outer surface of the steel component while leaving the inner core softer and more ductile. So let's take an example of an alum shaft and bush. So in this setup, the alum shaft is case hardened and chrome plated. And the reason of this is that only the outer surface of the shaft need to be hard to resist a scratch or penetration from the balls inside the alum bush, which roll along the shaft during the operation. Inner core of the shaft, however, is left softer and more ductile. The softer core provides the necessary flexibility and toughness to withstand the heavy loads without breaking suddenly. If the entire shaft were full hardened, it would become brittle and could break under heavy load or impact. So by case hardening, we ensure that the shaft has a hardness, wear-resistant surface while maintaining a tough and ductile core, reducing the risk of sudden failure and enhance the overall durability. And the case hardening can be achieved by the various methods. So let's start with flame hardening. In flame hardening, the steel surface is heated by an oxyacetylene flame or other high temperature flame and then quenched to form a hard martensitic layer. This method is used for the large components like large gears, track for the heavy machinery, and the crane wheels. The main advantage of flame hardening is its flexible and mobile process, suitable for the large component and localized hardening. In induction hardening, the steel component is heated by electromagnetic induction and quenched to form the hard martensitic layer, and this method is used for the shaft, axle, gears, and bearing race. However, it is limited to specific geometries. Next, we have carburizing. In carburizing, the steel is heated in carbon-rich environment, often provided by the gas like methane or propane, or solid carburizing compounds, allowing carbon atom to diffuse into surface and increase the carbon content. And this creates a hard wear-resistant surface while keeping the core softer and more ductile. Carburizing is ideal for automobile gears, camshaft, crankshaft, with case depth with hardening depth range from 0.5 to 5 mm. Next is nitriding. In nitriding, the component is heated in nitrogen-rich environment such as ammonia, forming high nitrides on surface, and this produces a hard surface with minimal distortion and stress. Nitriding is used for engine components, aircraft's parts, and high-performance tools with case depth from 0.1 to 0.6. Very thin case depth. Next is carbonitriding. It is very similar but involves exposing the steel part to the both carbon and nitrogen gases and create hard wear-resistant martensitic layer. This method is faster than traditional carburizing and providing case depth between 0.075 mm to 0.75 mm. Very thin case layer, and making it suitable for small components like a screw, fastener, and hard gears. Lastly, we have cryogenic hardening. This method involves cooling the material to extremely low temperature using liquid nitrogen, minus 185 degrees centigrade, typically after conventional heat treatment, and provide extremely high hardness level like 80 to 90 HRC on tungsten carbide. Cryogenic hardening enhances the wear resistance and performance of the engine parts, gears, bearings, also in sports like golf clubs and hockey blades. I hope I have covered all the hardening process in this video, but yes, I have not covered edge hardening, because it is mostly preferable for the aluminum alloy, not for the steel alloy. Maybe I will explain in another video. So this is it for this video, and thank you so much for watching this such long video.